in your
All right, so let us start. Last time we talked about some properties of number systems, right? Basically, we start from 0, 1, and then we start defining natural numbers, and then integers, and then rational numbers, and then irrational numbers, right? And in addition to that, you know that when you have real numbers, you usually talk about intervals, right? Right, so we should usually talk about intervals. Hello. Okay, so we usually talk about intervals, right? So you know, in a real number system, you can always represent an interval, right, in different ways. Right? So let us just define them, right? Right, so basically you studied about order relations, right? So you studied about order relation, less than, equal, less than, greater than, equal, greater than. So here, those relations, especially the order relation, right, it creates certain subsets of real numbers, and those subsets are basically called as intervals, right? See, for example, A less than B is an order relation, right? So that basically creates an interval in the real number system, right? So you must have learned this at your, right? So this is how you denote interval, right? At very low level, you write down these intervals, right? But basically, it's the product of these order relations, right? So that's the consequence of order relations. So similarly, you know, there are other types of intervals as well, right? closed interval. In an open interval, if you include endpoints, then that becomes a closed interval, right? So here A and B are not members of the interval, right? Because everything strictly greater than A and strictly less than B, right? But when you make the endpoints also the members of the interval, then the interval becomes a closed interval, right? So that's how we do, right? So, and generally, you can create interval with one side being infinity as well, right? So okay, so real numbers goes all the way up to infinity, positive and negative infinity. So the way to include infinity is to put an open interval at the end because infinity is not defined, right? So you can create the open interval or closed, one side closed or other side open is also fine, right? So you can make this interval as well, right? So a comma infinity is also possible, right? So that is x belongs to real numbers at that x greater or equal to a and vice versa. Minus infinity comma a is set of all x in real number set that x is equal to a, right? So these are also possible, right? So you can have closed on one side and open on the other side, right? But whenever you have infinity, the interval should be opened there, right? You cannot have a closed interval at infinity. So based on this, you can notice that basically the real number system is a interval from negative infinity to positive infinity, right? So this is how you can define the intervals, which is basically a consequence of the order relationship which we have already studied. So now what we are going to do is to we last time in the last class I just gave you an exercise to see whether square root of 2 is a rational number or not, right? So actually you could have shown that square root of 2 cannot be written as a fraction. So in that case, it becomes an irrational number. But you can notice that square root of 2 satisfies all the other properties, right? So you can work on all the other properties, the algebraic properties, which is involving plus and dot, right? The product. You could have done anything, any of those properties by using square root of 2, right? So all those properties works for square root of 2, right? And then order properties, you can write less or equal, less than, greater than, involving square root of 2, right? So for example, you can write square root of 2 is strictly less than 2, or square root of 2 is strictly greater than 1, those kind of things you could have easily write it down, right? Or you can see you can multiply square root of 2 with some number and that is same as multiplying the reverse order. All those axioms, right, perfectly works for square root of 2, right? But still square root of 2 is not a member of rational numbers, right? So or even though all the axioms works for a certain number, that it still stays outside the rational number system, right? So that kind of gives us an idea that what the axioms we studied so far are not enough to categorize all those things, especially the infinity and everything, right? So that's why we are going for another axiom, right, which is known as completeness property, right? So in the next section, that is what we are going to do. We are going to start talking about the next chapter, that is chapter 2, right? We are going to start talking about completeness property, right? So that is where we will talk about upper bound, lower bound, and other things, right? So let me start the completeness property now. Right, so this is going to be the axiom number 3, right? So right, so axiom 1 is algebraic properties, right? Addition and multiplication. Axiom 2 is order properties, right? So we did that, and now this is about axiom 3, that is the completeness property, right? So we will talk about what do we mean by completeness property, right? So we will try to build up things in a towards the completeness property, right? So we will one by one we will define some terminologies, right, that are going to be used in this section, right, which will be eventually goes to this completeness property. So first we are going to define what do we mean by upper bound. Right, so let me define what do we mean by upper bound, right? So in order to define an upper bound, right, right, so we come down to a non-empty subset of real number, right? S be a non-empty subset of real numbers, right? So obviously if it is non-empty, there are some elements, right? And because it is a subset of real numbers, it satisfies the order property, right? So you can compare any two elements in the set, right, using the order property, right? Right? So a real number u, right, it not necessarily inside the set, right? So you can notice that I just say real number u. I only write belongs to s and I erased it because I want to enforce that number u may not be a member of the set, right? It might be outside the set, right? But it is called an upper bound if it is greater or equal to all the elements in the set, right? Say for example, we have a set S like this, right? So S is an interval from 1 and 3, right? 3 is an upper bound. 4 is an upper bound. Right? You can develop or you can find several upper bounds, right? For the set, because you can go outside the set as well, right? And because it is basically a subset of real numbers, right? So you know you are writing real numbers in the increasing order, right? When you are writing interval, you go from small to large, right? So once you get the interval, you can find several upper bounds for a set, right? Subset of S. So that's the first terminology, upper bound. Once you know upper bound, you can define lower bound as well. Right, so number L is said to be a lower bound of S if L is smaller than all the other elements in the set, right? L is smaller than all the elements in the set, right? So in the same example, right, S is equal to 1, 3, right? 0 is a lower bound, right? 1 is a lower bound, and so on, right? So you can say -1 is a lower bound, -100 is a lower bound. It doesn't matter, right? So as long as every element in the set is larger than the lower bound, it is fine, right? So any element which is smaller than or equal to all the elements in the set, it is called lower bound. So there is an upper bound and a lower bound for a non-empty set, right? So once again, as I said, you can think of upper bounds and you can think of lower bounds of the set. Okay, so once you know there is an upper bound and a lower bound, right? But so now I gave you an interval here, right? So that there are upper bounds and lower bounds for the same interval, right? But you should know that not every subset of real number has upper bound or lower bound, right? Especially, right? Just as a note, the set of natural numbers, right? You have a set of natural numbers, right? Right, this the set of natural numbers cannot have an upper bound, right? You can easily check that, right? So it's not a big thing, just a hint. I will give you the way how to prove, right? Let U be an upper bound. In, right? So if it has, so we will come back to that later, right? It's maybe a little too much for you to think of the proof here, right? So we will come back whenever we are talking about supremum and other things, right? So now we just say that there is upper bound, there is lower bound in a set, and there are sets which cannot have upper bound. There are sets which cannot have lower bounds, right? There are sets also there, right? So not necessarily all the sets have bounds, right? So some of them may not have upper bound or lower bound, right? So once you know if a set has an upper bound, then we can call the set bounded above, right? Right? So if S has an upper bound, then we say that S is bounded above, right? If S has a lower bound, then we say that it is bounded below, right? And then if it does not have an upper bound, then we say unbounded above. And if it does not has a lower bound, then we say it is unbounded below, right? So those terminologies basically it's similar to what you have in English, right? So when you say bounded, and if it is bounded, if it has an upper bound, you say bounded above. If it has a lower bound, then you say it is bounded below, right? If it does not have an upper bound, you say it is unbounded above. If it does not has a lower bound, you can say it is unbounded below, right? So mostly bounded above and bounded below are the two terminologies we will stick with, right? We very rarely use the word unbounded above and unbounded below, right? At this course. So now you see that there are many upper bounds, right? But if there is an upper bound for a set, you can see that there are many upper bounds and there are many lower bounds. So it is good if we can find some special type of upper bound, right? So there are a lot of upper bound, there are a lot of lower bound. So it is hard to handle all of them. So we will try to come to one of the best possible upper bounds and the best possible lower bounds, right? So those has special names, right? So we will define the best possible upper bound, right? It is called suprema. So this is a new terminology you are going to encounter in this course, right? Upper bounds and lower bounds you might have heard earlier, but supremum is a new term. So let me write it down. And supremum. Supremum is basically an upper bound, right? Which has some special property, right? So it is a special type of upper bound. So I'm using notations here, right? S is a non-empty subset of R, right? S is a subset of R as well as it is non-empty. So that means S is a non-empty subset of R, right? If S is bounded above, if S is bounded above, then you know it has upper bound, right? There should be at least one upper bound for S, right? Among those upper bounds, right? If S is a non-empty set and if it is bounded above, right, the least upper bound, right, there can be many upper bounds, but among those, the smallest number, the least upper bound is called, right, the least upper bound of S, right, I can say S is called the supremum of S, right? We write it, right? Right, so we write it as sup S, right? This is the notation we are going to use for supremum, right? So instead of writing supremum in full, we will say sup S, right? So that means it is the least upper bound of the set. So that is the least upper bound. So if there is a least upper bound, right? So obviously similar type of thing should be there for lower bound, right? So that is called infinite. Right? Infimum. Infimum is the largest lower bound or greatest lower bound. Right? So when the set is bounded below, there will be lower bounds, right? Among them, you pick the largest lower bound, right? So when you pick the largest lower bound, that is called the infimum of the set, right? So we denote it by S, INF, right? Inf of S. That means infimum of S, right? So say for example, you have an interval like this, right? So let me say AB, right? Everything here are upper bounds, right? Everything here are lower bounds, right? So, but the best possible is you come all the way down and come here, right? So this basically superfest, right? If this is the set. So that is the smallest upper bound or least upper bound, right? And then in the lower bound case, right? So everything here are lower bounds. So you have to go to the largest lower bound to get the infimum of x, right? So that's and so this is the idea behind supremum and infimum. Now basically, you should know the terminology and you should know the meaning of that, right? So supremum is the least upper bound and infimum is the greatest lower bound. Right. So first thing is, because now from upper bounds, right? So there are several upper bounds. We come down to supremum, right? So the least upper bound. So you can kind of intuitively think that okay, if there is if we call the least upper bound as supremum, right? Then there should be only one such bound, right? Then there cannot be two supremums, right? So if there are two supremum, then you have to think, okay, which one is the least, right? So that's the idea. So obviously, intuitively, you know that if there is a supremum, then that should be unique, right? Similarly, if there is an infimum, you should know that it is unique, right? But we can always prove it, right? It's not a big thing. You can just prove it. So let me write down that statement and then try to prove it. Right, supremum as well as infimum, right? So, and it is first thing it should exist, right? So that means in a non-empty set, if you have upper bounds only, you can talk about supremum, right? If it is not bounded above, then you cannot talk about supremum. If it is not bounded below, then you cannot talk about infimum, right? You can talk about supremum and infimum only when the set is bounded above or bounded below, right? If there is a supremum, if it exists, then it should be unique, right? So let's say there are two supremums, right? So we will prove it. I'll show it for supremum. You can easily do it for infimum, right? Supremum. Right, so let's say U and U bar are the two supremums of S, right? Right, if because U is the supremum of S, it should be the least upper bound, right? If you say U is the supremum of S, then that means it should be the least upper bound. So it should be smaller than any other bound, right? So U dash another bound, that is also we say it is supremum. So anyhow, when you take U as a supremum, it automatically becomes smaller than the other bounds, right? So that means U should be less or equal to U dash. Similarly, because U bar is also a supremum of S, it should be the smallest. So that means it should be less or equal to all the other bounds. So that means U bar should be less or equal to U. Okay? So it is only possible whenever U and V are equal, right? So that's not a big thing, right? Even though you can figure it out intuitively, just if you want to prove this mathematically, you can argue in this way, right? Because if U is a supremum, it should be the smallest upper bound, and because U bar is a supremum, it should be the smallest upper bound. So one says U is less or equal to U dash for U bar, and the other one says U bar is less or equal to U. So when you combine both of them, it automatically gives you that U is equal to U bar. So that means supremum is unique, right? Similarly, you can say infimum is also unique, right? Right, so I will give you one example of supremum, right? Later on, we will see in one of the classes later we will try to see how to find supremum, right? Just to inform you that I will give you this exercise and just to give you an intuitive feeling about what do we mean by supremum, right? So let's say S be the set. Right, so let S be the set of numbers of the form 1 upon n, where n belongs to natural number. Right? So you can just write down the set. Right? So at the beginning, just to see how the supremum and infimum works, right? You can write it down. Right? You can see that it is 1 upon 2, 1 upon 3, and it keep on going like this. Okay. So you can eventually see that all the numbers in the set lies in between 0 and 1, right? So you can see that this actually goes to 0 but not 0, right? You can see that it is actually going to 0 but not 0, right? So you can clearly see that. Right, so any number in the set S lies in between 0 and 1. Right, so these are the endpoints of this set, right? So it stays in between 1 and 0. So intuitively, you can see that the upper bound, the smallest upper bound you can have is 1, right? Because all the elements in the set is less or equal to 1, right? So that means 1 is an upper bound, right? And any other upper bound you find for this set are bigger than 1, right? So you cannot find any number smaller than 1 and an upper bound, right? Because 1 is also a member here. So all the elements are less than or equal to 1, right? But you cannot find any number smaller than 1 that can be a upper bound for this set. So clearly you can see supremum of S is 1. Similarly, you can see infimum of S will be 0, right? Because all the elements in the set are bigger than 0, right? And the greatest possible lower bound is 0. You cannot, if you go little above 0, right, that becomes a member in there. There should be a member in the set, right? Later on, we will argue why this should be 0, right? I will later on teach you how to mathematically argue and say this is the upper bound or this is a supremum and this is the infimum, right? But as of now, just for your just to see how the supremum and infimum are there in a set, we can consider this example and see that the supremum can be 1 and infimum can be 0 for this set, right? But so this is an example. Now what we are going to see is we are going to see an equivalent form of supremum that we can use to argue or argue or try to prove the supremum of a set or infimum of the set, right? So alternative. Equivalent forms of the supremum and infimum, right? So It's always SVL one empty subset of real numbers. That is how we start, right? So if A x is less or equal to 2 for x in S, B is less than U, and where x is x naught belongs to S, so that B is less than or equal to x naught. Right, so this is an alternative definition. Right? This is another way of defining supremum. Right, so actually the real definition is supremum is the least upper bound. Right, and this is another way of writing the supremum. Right, so any element in the set is less or equal to the supremum, and if you go little below the supremum, right? If you go little below the supremum, then you will find the element in the set, right? So here is how pictorially you can say, right? Now this is a set AB, right? So you obviously know this is your supremum, and this is your supremum S. So any element in the set is less than or equal to U. That is condition number 1, right? Earlier in the definition we see that supremum is the least upper bound. Here they say if you pick a value smaller than U, right? So if you go little below this, right, and draw a line B, right, you will at least find one element x naught, right, in between U and V. Okay, so that is what we mean by supremum, right? Because supremum is the least upper bound, so that should be very close to the last element, the largest element, right? So if you go little down, right, so if you go little down from the supremum, right, you can see at least one element jumps in between the supremum and the line you draw below. Right? So that's how alternatively we define supremum. Right? So similarly, you can define right. Similarly, you can say that if L is an infimum, if and only if any element in the set is bigger than L, right? So that it's a lower bound, right? And then next one, it is the greatest lower bound. So if you pick any element, any value higher than the greatest lower bound, you can see at least one element falls in between the greater value and L, right? So here again, the same thing. And so this should be your infimum of S, right? So if you pick anything bigger than that, right? The bigger than the infimum, you can see at least one element falls in between that bigger element and the infimum. Okay, so this is an alternative way of defining supremum and infimum as well. Okay? So this is how we define supremum and infimum. Another thing is, so here we talk about upper bound, lower bound, bounded above, bounded below, and then supremum, infimum. But you already know two other terminologies in a set, right, from your very young age, maximum and minimum, right? Right, so you know or you heard about maximum and minimum as well in your life, right? So far, when I gave you a set, right? Say for example, if I say 1, 2, 3, 4, 5 is the set, right? You know maximum is 5 and minimum is 1 in the set, right? So you know that. Right? But that not necessarily equal to supremum and infimum, right? Some cases, infimum and the minimum may be equal, right? Supremum and the maximum may be equal, right? But it is not true for all the cases, right? Because you can see that in this example, right? Your supremum is outside the set, right? It is an open interval, right? Your supremum is the end point, and in an open interval, you don't include the end points, right? Here it is a closed interval, 1 and 5 are there. So in this case, the supremum is inside the set, right? So it is not necessary that the supremum and the maximum are same or exist, right? And the other case, so I will write it down as a note here. Right, so you should not confuse maximum with the supremum, right? Or minimum with the infimum. Both may be different. Sometimes there will be supremum but no maximum. Sometimes there will be maximum and things like that, right? So you can right, so the existence of supremum does not guarantee the existence of maximum, right? Say for example, infimum of 1, 2 is 1, but minimum of 1, 2 does not exist, right? Maximum infimum of this set is 1, but minimum of 1, 2 does not exist, right? So this is another important note you should keep in mind, right? Existence of supremum does not guarantee the existence of maximum. Okay, so now we build up enough to get to the important point, right? completeness property. Right, so it is also axiom 3. Right, so we call it completeness property, and sometimes we will call it as supremum property also, right? And it is basically the axiom 3 there, right? So it's very simple. Right, so it says every non-empty subset of real number, right, that is bounded above will have a supremum. Right? Definitely, every non-empty subset of real numbers that is bounded above will have a supremum. Right? So this is the completeness property or supremum property that guarantees the existence of a supremum. Right? As long as it is a subset of real number and it is non-empty and it is bounded above. Right? If these three are there, then it is guaranteed that there will be a supremum for that set. So similar kind of results we can develop for infimum as well, right? So every non-empty subset of real number which is bounded below has an infimum, right? So that is the similar type of results for infimum, right? But you know, axiom should be only one thing, right? So because we define the axiom for supremum, we can use this axiom to prove the existence of infimum for a non-empty subset, right? So in Monday class, I will try to prove the infimum property by using this supremum property. Okay? So I will stop here and then I will continue on Monday.